All right, the next topic in differential equations is called homogeneous differential equations. And the deal is that not everything can be solved right away with the separation of variables, getting all the x's with the dx and all the y's with the dy. However, under certain cases, we might be able to still solve the differential equation by some type of substitution, which we'll talk about here in just a little bit. But what does this idea of homogeneous mean? So let me scroll this up here a little bit. There we go. First off, what is a homogeneous function? A function of what is included here as degree n. So let's say you have some function of x and y, all right? And if you replace all the x's with tx and all the y's with ty, and in the process of doing that, if you're able to sort of manipulate it to the point where you get t to the nth power, so it could be t to the first, t to the second, n's an integer, multiplied by the original function of x and y, then it is considered homogeneous of degree n. So you have some original function f of x, y, which means it's a function of x and y. It's all mixed up. And if you replace all the x's with tx and all the y's with ty, and if you're able to turn that into the original f of xy multiplied by t to the nth power, then that's what we mean by a homogeneous function of degree n. So let me give you a couple of examples of homogeneous functions. So here we have a function, and I know you're used to f of x or f of y, but this is f of xy, which means on the other side over here we have x's and y's all mixed up. So this is a function of x and y. So we want to see if it's homogeneous. So what we're going to do is take that function, and everywhere I see an x, I'll replace it with tx, and everywhere I see a y, I'll replace it with ty. So that's what I have down here. So the function is now replacing what was in the x position, tx, and what was in the y position, ty. So I'll get, here's an x, I'll get tx, and that is being squared. Here's a y, I'll replace that with ty, minus 4 times, there's x again, it gets replaced with tx, and it's being cubed, so it's tx in parentheses cubed, plus 3, there's x, so it gets replaced with tx, and there's y, it gets replaced with ty, but it's being squared, all right? So there's 3 terms here basically. This first term, if I sort of expand it out by squaring the first thing and then do multiplication, I'll get t squared times t, or t to the third, x squared y. So that's my first term. My second term will be negative 4 times, and I'm going to cube tx. So I get t cubed x cubed. And then my last term, I'm going to square the ty, multiply it by tx and 3, and if you're careful, you'll get 3t cubed x y squared. So as I look at all 3 of these terms, they all have a t cubed in them. So I'll factor the t cubed out, and look at what's left in parentheses. It's x squared y minus 4x cubed plus 3x y squared. That's exactly what the original function of x and y was up here. So by replacing all the x's with tx and all the y's with ty, I ended up getting t cubed times the original function of x and y. So this function up here at the top is considered homogeneous of degree 3. All right. One more example here. Another function of x and y. This time x plus y squared. So I'm going to replace all the x's with tx and all the y's with ty. And if I do, I'll get, there's an x, so it becomes tx plus, there's a y, that becomes ty, and then I square it. So my first term is going to be tx, my second term would be t squared, y squared. So whenever I look at the 2 terms and the t's, I can factor out a t, but look at what's left. X plus ty squared. It's not x plus y squared. So this one is not just t times the original function. So this one is not homogeneous. All right, so that's how you figure out whether something is homogeneous or not. What does that have to do with differential equations? Well, this. A homogeneous differential equation is one that can be written like this. Now, there's a couple things to look at in the form. There's not a y prime or a dy dx, because you can see a dx here and a dy over here. So it's sort of been split up. The dy dx has been separated a little bit. In front of the dx, we have some function of x and y, which we call m sub x sub y, m at x sub y. And then in front of the dy term, we have n of x and y. It's also a function of x and y. And this is all equal to 0. So m and n are homogeneous functions of the same degree. So if this m at x, y is of degree 2, this one's of degree 2. You know, they have to match up. And if they are, they're considered not just homogeneous functions, but this is a homogeneous differential equation, because there really is a derivative in it. There's dy's and dx's. All right? So, if we have an example here, we want to verify that this differential equation, because it really has a dy and a dx in it, is a homogeneous differential equation. So what that means is we have to look at the function in front of dx and the function in front of dy and play the, hey, replace the x with tx and the y with ty game. So I'm going to go through this one kind of quickly. You can look at it if you need to. But over here I replace the x's with tx and the y's with ty, and I work it out, and I find that I can factor t squared out and then have the original function here. So this first part is of degree 2. Then I'll do it with just the y squared. This one's pretty easy. There's no x's to replace. So I'll replace the y with ty, square it out, I get t squared y squared. So this one really is t squared times the original function of y squared. And it is also of degree 2. So since the degrees of the homogeneous function parts of the entire differential equation match up, it is homogeneous. It is a homogeneous differential equation of degree 2. All right? So, how do we solve a homogeneous differential equation? Okay, how do we get the original y, which is a solution to that? Well, what you'll find is that almost always these type of differential equations are not separated. It's not like you have all the x's with the dx and all the y's with dy's. But we can convert it into a separation of variables type problem if we make a transformation. There's actually a couple of transformations. The first substitution we're going to look at is we're going to replace y with vx. So what is v? Well, v is some function of x. Just don't know what its form is. So it's a function of x that can have its derivative taken. And x obviously is x. So y is v, which is a function of x, times x. All right, so that's the substitution we're going to make. So if we do that, replace all the y's with vx and all the dy's with what I'll show you here in a second, we can turn the homogeneous differential equation into something that we can separate the x's and the dx's and the v's and the dv's out, perform separation of variable techniques, and then at the end substitute back out of the v's back into the y's. And that sounds like an awful lot of stuff, but that's what we're going to do. And we're going to look at that in the next video, because I'm going to stop this video at this point before I get into the problem. So this is part 1. You'll see part 2 shortly.